Well, welcome everyone. We're delighted to have you here today for a talk by Dr. Armand Neukermans. Thank you for agreeing to come. He holds an electrical engineering degree, a mechanical engineering degree, and a PhD in applied physics. So quite a brush of expertise. He's worked for as varied companies as KLA Tencor, Hewlett Packard, Xerox, and General Electric. He's an inventor of over 80 patents in very diverse fields. And in 2006, he set up in Portola Valley the Solar Community Project, which I've lived here long enough, I can remember that. Thank you. And he helped launch Solar City. So the last 14 years, he's directed a group of volunteer scientists and engineers on an innovative climate mitigation effort. It's in conjunction with the University of Washington and SRI. The group is doing technology research for cloud studies and marine cloud brightening with seawater. And it's to cool the earth and for particle dispersal for the Scope X Stratosphere project. Now this really intrigued me, being that we were looking at not just a geoengineering project, but it was a geoengineering project that was using not made up chemicals, but using something that's natural. So that really intrigued me. And when I asked him about himself, he said, well, I'm just a regular person who sees what's going on, and I want to do something. And I was lucky to find a group to work with. So to kind of introduce the whole idea of why these things are coming to the forefront, there's a quote from Jeff Masters, a meteorologist. He's a co-founder of Weather Underground, which I'm sure some of you may be familiar with. Okay. He was asked the question, do you think the wild weather this winter is going to continue? His answer, it's going to be bonkers this year. This summer in particular, we've got a record amount of heat in the oceans right now. That means this summer should be a record warm summer globally. And when you've got record heat in the atmosphere, that means a lot of energy to power extreme weather events. So we're going to see record heat waves, we're going to see record droughts and record rainfall events because you can evaporate more moisture into a warm atmosphere. And I'm really concerned about the Atlantic hurricane season too. If you look at the region of the tropical Atlantic where hurricanes form, the late January temperatures were the same as what we typically see in late July. So that's pretty insane that we had July-like ocean temperatures in the tropical Atlantic. Thank you, Armand, for coming to tell us about what might be possibilities for us, what we need to really start critically thinking about and thinking about now.
Thank you. Anyway, it's good to be here this morning. I try to make you not too depressed on this beautiful morning, but you know, the situation is what it is, as they say. So anyway, actually, in regards to this last rise of the ocean temperature, we actually may be actually seeing a decline gradually, because it looks like La Nina is coming in faster than we thought, fortunately for all of us. Anyway, so I'm going to talk a little bit about marine cloud brightening this morning. And maybe just turn that on for here. So actually, I'm going to talk a little bit about recent events in climate science and the urgency that's now appearing of to do some form of geoengineering. We sort of always had it in the background, but the last few months, people that have resisted it are start saying, we don't have a choice anymore. We're going to have to investigate it. That does not mean that we're going to do it, okay, because there are certain risks to it, and we all realize that. But it is very high time, actually, to do the research on it and see what works and doesn't work. So there are various forms of solar engineering, and some of them are, there is a new one every day in one form or the other. So I'll talk a little bit about our experimental work, and then obviously I welcome your questions and whatever else you may have in mind. So, I'm sorry. Okay, so these are layman's impression, okay? I'm not a climate scientist. I worked in a variety in the field, but not in climate science. So I've learned a lot from working at them in the last 15 years. And, as they say, you're looking into a very cloudy crystal ball. And as they say, it's difficult to make predictions, especially about the future, all right? You know that expression. So the best name for this is actually climate disruption. It's not that the temperature is going to go up and down. We're going to have a lot of variation. But the stable climate that we had for about 12,000 years, we're now endangering it at a very, very rapid rate. Okay? So the problem is that the potential changes that we're facing are so deep that it's very difficult for us to accept it. We have experienced that go a lifetime, or centuries, so to speak, of what we have in history, and this is different. And we genetically aren't really made to accept that very well. That's the real problem. When there is a bear or a Russian bear, we sort of know how to deal with that. But this is something that's very gradual and something very innocuous, and we're not prepared to deal with it. And so it's like Bert Richter, the former director of SLAG, said, this slide is now 15 years old. He said, it's the only field where the experts are more worried than the general public. We're worried about atomic energy and all that other stuff, whatever. And so Stephen Salter, who was sort of the climate, he and Jim Hansen were the most renowned climate scientists, unfortunately passed away 10 years ago. So the truth is bad enough, essentially, we shouldn't exaggerate it. And actually, it's our own inaction that is by far the largest danger. So there's some disturbing recent insights that are only a few months old, right? So the first thing, I didn't write it all out here, but you should probably look at this thing from YouTube, from Jeffrey Sachs. I'm sure some of you know Jeffrey Sachs. He was the one that set up the millennia criteria, right? So around 2000, they set up, he was at Columbia University and head of the Harvard Institute. And he set up the criteria to basically reduce poverty and whatever else over the next 20 years. Unfortunately, we haven't gotten there, but that was a very, very idealistic proposal. So this is an optimist, okay? When you hear him talking, this is an optimist. So that's why you actually should look at this YouTube from Jim Hansen. So Jim Hansen is the foremost climate scientist in the United States. That doesn't mean that's infallible, but usually the stuff that is presented in the past has come to pass. So we have a quantity that you call climate sensitivity, all right? So climate sensitivity is what happens when I double the amount of CO2 that's in the atmosphere. So traditionally, that's been, before the industrial revolution, was for centuries about 280 parts per million. It's not always that, but it's sort of like that. So now the number of CO2 that we have in the Earth is about 420 parts per million and growing by the day. Maybe it's 430 now. But the real thing is that if you add up all the other stuff that we have, the methane essentially, we're sitting at 520 parts per million equivalent of CO2, all right? That's not very far from doubling. So if I take all the CO2 away here of Earth and all the clouds, all right, the temperature would be minus 20 degrees C. That's about minus 25 Fahrenheit or something like that, okay? So if I add in the CO2 we're starting and clouds come up and all that side, then it goes to what we have now, about 15 or 16 degrees C. That's what we experience now. So the question has always been, what if we add this other 280 parts per million, okay? What's gonna happen? What's the temperature gonna be? So people have calculated this for a long time. Actually, since the 1840, okay? When people started knowing about radiation, Fournier in France, 1840, became aware that there were gases there that are absorbing the heat coming up, because otherwise we would be sitting at minus 20 degrees C, which wasn't true. So anyway, so people have calculated, and the first one was Arrhenius, which some of you may remember from your chemistry books. You always said, you know, Arrhenius at one time or the other. And he calculated that it was about 2.4 degrees C, about 2.4 degrees C. It's a very long calculation by hand. And it's remarkably accurate. And he thought, well, you know, that's a good thing. I mean, he lived in Norway, and so he's in Sweden. Oh, this is a good thing. That's going to be good for the Earth, all right? So we didn't worry about this for a very long time, all right, until we started measuring the CO2 and start seeing that it's going up. And then we did start to measure. So people now, they're about, you know, there is an IPCC, this is a commission that puts out a report every 3, 4, 5 years. And they take about 30 climate models, right, the best climate models in the world, and they aggregate them and they see what they come up with. So these climate models give very different results because the way that you deal the clouds. Why are the clouds difficult to deal with? Because the clouds contain supercooled particles, and they reflect different from ice in the frozen. You all know that ice freezes at 0 degrees C, 30 degrees Fahrenheit, but that ain't true. It's only true when there's a lot of other things that make it freeze at the time. If you have a small particle like you have in the clouds, you can cool it to minus 40 degrees C. That's minus 40 degrees F, and it won't freeze, all right? And then if you give it a little tickle, it freezes all at once. And that changes the properties of reflectivity of the clouds very, very difficult. And that's why this whole thing is so difficult to really get a very good grip on it. You know, so anyway, about 4 or 5 years ago, newer and better models started coming up, and they say, well, you know, it's not 2.4 degrees C or 3 degrees C or whatever it is, okay? It's 4.5 to 5.2. Now, that's curtains, okay? I mean, it's curtains for a civilized society, okay? We can't cope with that. I mean, that's a well-established fact. So that's a very alarming fact, okay? And so if you extrapolate this, if you take how much CO2 there is now, and you go back in the Paleolithic time, you come to 8 degrees C. But, you know, this is hundreds of years away. We probably will have to deal with that. But in the short term, okay, we're looking at something that if you double, okay, this is going to be here, you know, if you think about it, it's going to be here in 20, 30, 40, 50 years, okay, depending who you believe. So these climate models, there are 5 of them. These were the newest ones and the best one. And they say, well, we won't take them in because they're really so far off, we won't take them in. Until somebody had the good idea, one of these climate models can also measure the weather. It's a very different thing, but it's a very short time, right? So there was the Met Office thing. And they did. And they found that these climate models actually measured the weather much better than anything else that we had before. So that gives a great amount of credibility to these new climate models. And so this is why so not everybody believes Hansen, but this is why people now start saying, wow, this is serious. And so until 2020, you know, everything was sort of fine. The project that we worked on said, well, this will be fine for our grandchildren. We don't have to worry about this. Still there. Well, in 2020, everything changed, right? You saw all these effects left and right, et cetera. And so now we're rising very rapidly. And so the effect of this is that the reason that we don't see this yet, okay, is that we are protected, okay, by a layer of sulfate that's made by all the fossil fuels, okay? So if you burn coal and whatever it is, you make a lot of fossil fuels, that becomes a sulfate, it stays in the troposphere, and it acts like a sunshield, all right? That's why we haven't seen that. The tragedy is that we have to take that away because we have to get rid of fossil fuels. And that actually is going to make the temperature rise twice as fast as it does now. But we don't have a choice. So this is why we're trying to come up with another solution, another shield that is not depending on fossil fuels, but has the capability to be put up in a reasonable short time and all that kind of stuff. So I want to emphasize again, what we're doing or what these people are trying to do, it's not a long-term solution, okay? It's something you're coping with in a very short term, but it could make a hell of a lot of difference, essentially, in terms of where we get in the future. So there is a lady here, Sabine, she is an English physicist, and she explains these things remarkably well. So anyway, I'll send you this information if you want. Next slide. So what is geoengineering? And so it's sort of not a, it's not a very good term, but people don't like the term. But anyway, it's a deliberate judicial intervention in the climate system. And so even when we tried to mess around with the matter, okay, it didn't work very well. So the first time, somewhere in the 1850s, we tried to actually seed the clouds. Okay, what we're doing is not seeding the clouds, and we did. And there was, that year happened to be 100 atmospheric rivers, okay? So it dumped the whole Central Valley, was underwater in the 1850s. So many of these experiences, since haven't worked very well. So for example, there was a hurricane that we tried to seed one time. And so it's coming straight for Florida to seed it, and then it goes north. That was the end of the hurricane seeding and all that kind of stuff. So, you have to be very, very careful when you do this, etc. So it's imperfect. So it's a stopgap measure. And it's certainly not a substitute for decarbonization, okay? The only geoengineering method that's ever going to work, okay, is take all the carbon back out, okay? So you have to take all the carbon back out. That's what we got to do. Unfortunately, we don't know yet how to do that. There are people that try to do this mechanically. That's going to be very challenging at this starting because you need a lot of energy, right? I mean, it's just a tiny little bit. There's only 1 in 10,000 molecules that consist of CO2. But you have to move them, bring them all here, essentially, which requires a lot of energy. So this sort of, people have sort of known this, that we could do this since a long time. But in 2007, Paul Crutzen, who was a Nobel Prize winner for the ozone layer, right, made a proposal, and he said, look, all these, we said, all these thoughts that we have about reducing the carbon emission and all that kind of stuff, they're pious thoughts, but they're not going to work in time, all right? And so, he was a very respected guy, and so people knew that these guys start supporting this, then basically, the ball is rolling, right? So actually people asked him not to publish this article, and eventually what was settled on, he published this article, and next to the other page was another article saying why we shouldn't be doing this, okay, because of all the consequences, etc. So, it sort of seems like a bad idea, unfortunately, whose time has come. That's one of the best ways to sort of specify this. Oh. All right. So you've heard of the Anthropocene. Actually, the Anthropocene was a term that was coined by Paul Crutzen. And it's basically saying that we know the driving thing and the driving force in the geological time, right? And so it's also the age of man, that's what it means, the age of man, that drives the thing. But it's also the age of consequences. And that's, that goes back to the famous speech of Turtle in 1936 that, we're now entering a period of consequences. And why is that, okay? It's with the cumulative effects of CO2, all right? And it's very hard to remove. That's really why we're doing it. So let me give you some facts that your mother probably never told you about CO2. Okay? So I take a piece of coal here because I want to heat the room, all right? And I get the coal up, and that's wonderful, right? Okay? So then, I get a little bit of smoke, the CO2 you don't see, then you think it's all over. Well, it's just starting, okay? That CO2 goes in the air, all right? And after 30 days, that CO2 has generated the same amount of heat in the atmosphere as you got out of here in the room, okay? After 30 days, all right? Unfortunately, that's not the end of it. That repeats every 30 days for about the next 10,000 years until the CO2 is gone. Those are the consequences when you think of it. When we drive away here, all right? This stuff that will leave in the air, that's going to be there, not just for our grandchildren, but for generations, okay? That's the cumulative effect that we're dealing with, okay? And so the multiplication factor of this heating that we get over here could reach 100,000, okay? I'm sorry. So the CO2 is going to be with us for a long time. If you have nuclear energy, okay, after 1,000 years, that's a long time, it's down also by 3 orders of magnitude. But if you put CO2 in the air, okay, depending on how much you put in it, all right, it goes down by a factor of about 1.7 in 10,000 years. That's the difference. It stays there. It takes a very long time to weather all this away. So yearly, we put in about 40 billion tons of CO2 in the air, right? 40 billion tons, plain CO2. So that, what does that represent, all right, 40 billion CO2? I'll tell you what it represents. You take an area the size of Africa, okay, and Europe combined, okay? 40 billion acres, okay? And every acre during a mature forest fires produces 4 tons of CO2, okay? That's 40 billion tons. That's 40 billion tons. That's what that means. Every year, you produce a forest fire, a mature, plant all of Africa, free mature trees, and Europe set them on fire. That's 40 billion tons of thing. And you don't have to be a geophysicist to know that that is not a good thing, that there's going to be consequences of that. And that's what we're experiencing now. So, so in 2015, we had the Paris Accord, right? And so it's a very good thing. Don't let me knock it, all right? It's a very good thing. But, we said, all right, we're going to hold 2 degrees C, all right? That was the general consensus. That is sort of maybe we can do. Well, it turns out that all the countries that are getting underwater, all the islands in the Pacific, they say, that doesn't deal for us, okay? And so, they started screaming. And so they said, all right, well, this is how it went, okay? Let's make it 1.5, all right? So, I don't know, I have the pointer here. Anyway, over here, there, you see January there? So in December before that, okay, 2015, that's what the thing was. This is what happened to the temperature, global temperature, 2016, okay? See that black line there? Where it's saying? That's when it was signed, okay? We almost reached already 1.5 degrees C, all right? You know that if that happens, okay, promising that you're not going to reach it in 20 or 30 years is just for the birds, right? So we're deluding ourselves. So there are various forms of, greenhouse emissions, essentially. And this is, this is not a very well-known science. Very well-known. There are a lot of things that we're still figuring out on the fly, okay? So the parts on the left, these are all those that does radiative forcing. We absorb radiation and it forces us back on Earth, all right? And so all the left is what gives us hotter and hotter. And then on the right-hand side, what you see over here, I don't know if you can read it, that's the aerosols and that's the clouds. And those have very large error bars. So when you add it all together, okay, you see the red bar, that's when you're all together. It pushes the heat up, okay, the radiation. But there are very large error bars. If you go to the lower, you could have 3 times less than on the other end of the error bar. And so this is essentially what we're still figuring out. So what we're doing in the meantime, all right, we're basically duct taping now the Alzheimer glaciers, okay? That's a proposition of about $12 million square kilometer, all right? That's what we're doing to preserve it. And I'm not knocking it, all right? And I don't know if you've ever been to the Rhone glaciers. And actually, while they're still there, I recommend it. It's on the Furka Pass in Switzerland. And you walk in under into it, and it's the most intense blue experience, okay, that you ever experience because of all the Rayleigh scattering anyway. So that's covered now. If you don't have that kind of money, this is what you do. You basically whitewash the tops of the mountains, hoping that this will reduce the temperature and keep the snow the thing. Because all the southern part of the mountains in South America, that's what they're experiencing. That's all going to melt, hopefully not too fast. It's the same with the Arctic mice, the prediction at the moment is that about 2030, okay, the Arctic will be ice-free. That doesn't mean that there is no ice, but it means that you can fare through it with a ship without any problem. So, what's 2 degrees C? It doesn't seem like a big deal, right? I mean, one day the temperature is this, and one day the temperature that. I hope you still know a little bit of statistics, okay? So what you see there on the left hand, this works best for temperature. What you see there on the left-hand side is what we call a Gaussian curve, a normal distribution of events, right? So most of the time, at this time, in this day, I expect this temperature, all right? And then sometimes it's less, etc. And the number of events, the ordinate tells you how often you can expect that. And so the normal temperature I expect that. And then you know what the standard deviation is, right? So you move one standard deviation, all right. So what we have now done, that you can see there on the green curve and on the purple curve, we've displaced that curve by 1 standard deviation, all right? So events that used to be 2 standard deviation aways are now only 1 standard deviation. And events that used to be 5 standard deviation away are now 4 standard deviation, okay? That's really what we are experiencing now, all right? So events that happened, yearly events, they now happen every 3 weeks, okay? The events that happen, twice in 100 years are now happening yearly, all right? And events that happen every 5,000 years, okay, are now going to happen twice in your lifetime. This is just one sigma. For the moment, we already are 1.5, okay? So this is why we have this, these events happening that we say, well, that never happened before, etc. And so, if you live in the jungle, to recover from an event like that, it's pretty easy. But wherever you have the very complicated and expensive infrastructure is, and it gets destroyed, keep on rebuilding this time and again is actually, that's quite a job to keep this up. So that's why people start looking at solar radiation magnet. I'm not going to explain all this essentially, but you have incoming sun, then some of it is absorbed, and then some of it goes back out, right? So what people are now proposing is saying using particles to increase the reflection of the sunlight in the atmosphere and therefore reducing heat. And you can do that in one way. In the top one, you see that you put particles in the stratosphere, all right? That's one way of doing it. And the second one is you whiten certain amount of clouds that are low-hanging clouds over the ocean. And the reason, so the stratosphere, we live in the troposphere, right? In the troposphere, there is continuous circulation. If I put a particle over here, it's going to turn around in a week and be down, okay, no matter where I put it up. In between the stratosphere and the troposphere, there's a very stable layer that's very difficult to penetrate. And above that is the stratosphere. In the stratosphere, everything moves like this. It glides, okay, at hundreds of miles speed an hour, okay? So if I put a particle in the stratosphere, all right, it falls down. But if it's 1/3 of a micron, it takes 2 years to fall out of the stratosphere. That's how long it stays there, all right? If I put a particle in the troposphere, it's going to circle around in no time, and in a week it's gone. So that's the difference about it. So we know this because of the volcanic explosion, right? So, and the other one, the cooling that we see by emissions. So there are presently 2 viable SRM methods. There are other methods that are used locally. Okay? One is that you put about 1.5 million tons of particles in the stratosphere, and these are individual particles that scatter light. We know what that physics is, and we can calculate pretty well what the effect is that going to be. So that's long duration, and it's sort of like a volcano, right? And the other one is the one that we've been working on, is marine cloud brightening. So you spray ultrafine droplets of seawater at sea level. They sort of hope you drift into the clouds if the conditions are right, okay? So the clouds get denser and wider, all right? And this is sort of, it only lasts a week, all right? It's very localized, and you do it on a small scale. So the problem with doing experiments in the stratosphere is that you can't do, it's very difficult to put a small scale experiment, okay? If I wanted a cloud, the ones here in Half Moon Bay, I can do this in Half Moon Bay. But if I put a particle in the stratosphere, an hour later it's 200 miles further, and so that, that's because of the speed. That's where the jet stream is, anyway. So these might be used together in one way or the other, etc. And as I say, they're imperfect. They don't do anything about, when there's a lot of CO2 in the air, the ocean becomes more acidification, and that's got a lot of consequences that aren't good either. And so it doesn't do anything about that. So these are all imperfect situations. So we had Mount Pinatubo in 1991. Some of them may remember it. We had these beautiful sunsets. That's what happened. You get the stuff in the stratosphere and things like that, etc. Well, that set the Earth back. It cooled it for about 0.7 degrees, about 2-3 years. Now, we have had other things in the past. In 1815, I don't know, you remember from your history, but the wash used to freeze in August essentially everywhere in the United States without a washing line. That was the main thing. So there was famine in many, many parts of the world for about 3 years. And that's because we actually had Mount Tambora that exploded, all right? And that put a lot more stuff in it. In about 75,000 years, we had Mount Toba. There's no question that it exploded and put millions and millions of tons on a different scale. And that wiped out, according to one theory, most of humanity, even though we were on Europe. So only the ones that survived actually survived in the south of South Africa and survived there in the thing. So anyway, that's on one or the other will work. So what's the advantage? So you have to bring up, sulfur, okay? And not only sulfur. You actually have to bring up sulfuric acid, okay? That doesn't look like a great idea to spray sulfuric acid. But let me tell you, compared to what we do now, okay, in terms of the sulfur, it's a small part, it's a fraction of a percent of what we have now from all the coal plants, okay? So you want a particle so you need to bring out a couple tons, okay, every year. And this technology seems feasible. The only problem, so actually diffuse light, that diffuses the light, that makes the plants grow better. So you notice each time that there will be some sort of volcanic eruption, okay, that year the plants grow better. So diffuse light is better for plants than direct sunlight. So the cost is very modest. It's modest being $10 to $20 billion a year, all right? And that's why this is so attractive. And so it's doable, but it's also dangerous. I mean, as the more we learn about it, the dangers seem to go less, but it's something that we can't do without really extensive experiments. It's not easy to sell to the public that you're going to spray this sulfuric acid in the stratosphere, right? It's difficult to do on a small scale. You can't undo it, all right? And that's not necessarily true. Once the particle's up there, they're up there for 2 years, right? That's not necessarily true because with calcium carbonate, we thought of a method that we actually can, by charging and pull them back down. So, but there are other effects. The sulfur itself may deplete the ozone. Not very much, but a little bit. And let me tell you about the ozone, okay? You know how much ozone there is up there in the stratosphere? It's kilometers and kilometers thick, right, okay? But it's very diffuse. So if you take the entire ozone layer, okay, and compress it down, this is how thick it is, 1/8 of an inch. 1/8 of an inch of ozone, okay, is all that separates us between life and death. That's the reality. So we think that this is a very, very solid Earth system, right? Well, the more we learn about it, you know that, oh yeah, it is, as long as you don't mess around with it, okay? And so we had the ozone scare, right, where we chlorinated these materials, okay? So the guy that invented that, he also, by the way, invented the putting lead in the thing, right? The same guy. So anyway, they were thinking of brominating it. Brominating it worked also very well, all right? But it was a few cents more expensive. If we had brominated, okay, we would have lost the ozone layer before we became aware of it. That's the reality. 6 ton Leo Branscombe, okay, the head of thing, that 6 ton of bromine released in the northern atmosphere ruins our climate completely. So we have some scares had in the past, actually, that we only now become aware of. Anyway. So, the other thing is that when you do that, when each time you have a big volcano eruption like that, okay, there's a drought in Africa. How do you know that? We know that because the priests in Egypt kept very nice tables of the volume of the Nile flow. And they could say, oh, so we know when the volume is flow, there's a drought this year, right? Now the difference is this is a tremendous explosion all at once, all right? When you do this very gently, it isn't necessarily likely to happen. So would this work for us? Yeah, it probably would work for us, okay? So you see this here, the more I inject, the more the temperature is going to go down, all right? But once you are on this path, okay, you know, it's having a finger in the dike, okay? You have to keep it there, all right? And when you stop it, the effects are very, very unpleasant, all right? So once we commit to this, we're only going to do this if we have methods to suck at the same time, or starting to suck at the same time, the carbon out of the atmosphere. But this is the path that we are on. So marine cloud brightening is a different thing, so it sort of looks a little softer. This is conceived by John Latham, and then another famous English engineers joined them. So what you do is you start to reflect more incoming light from the source. So the story is that John was working with his son, walking with his son in Wales, and they came over the clouds, and his son said, hey, this is like a mirror. And that, he was an atmospheric scientist, and actually, so that's gave him the idea. He was a remarkable guy with a very tragic life, and a wonderful poet, by the way. So about 25% of the ocean, okay, has clouds that we think are suitable that you can be bright. A cloud that's very white, okay, there's no sense in making it any whiter, okay. So you look for clouds that aren't very white, and that's relatively easy to do. And so the perfect example is here of our coast of California. All the way from Patagonia until Oregon, essentially, those are the right clouds for doing this in the western zone. So we change this by a few percent, that would be enough to set the Earth altitude about 1%. So 1% of the sunlight is not a small amount, okay? But you have to realize that during the time that life began, okay, the sun's output has gone up by 25 to 30%, all right? So life started about 3.5, 4 billion years ago. The sun is a certain star. We know how it expands, how its energy goes. And during that time, we receive now 33%, or 30% more energy than when life began. So that sort of puts in that. Oh, I'm sorry.
We'll fix it. We missed the last slide.
Probably ran out of time. Am I running out of time? All right, yeah. There we are, okay. So, so this concept seems sort of more acceptable. It seems environmentally benign, You stop it, it's over in a week. It actually isn't, okay. If you keep doing things for years, all right, you're going to change the sea currents and all that kind of stuff. So it also has negative consequences, even though you think you can stop it in a week. That's not necessarily true. So there's another method, sky brightening, and that actually, so when you do marine cloud brightening, you make a very small droplet, very, very small. And that goes in the cloud. And in the cloud, it becomes a much bigger droplet that scatters much more. So we have a natural advancement. This is a rough course where you put up just salt in the troposphere, enormous amount of it, and that will do the same thing, and it will work. So, this has sort of gone from rogue science, essentially. We now have a papal endorsement. So in 2016, Oliver Morton, who was the science editor of the Economist, he published an article in Spray and Pray that it's going to work. And then Pope, of course, who has been a long time defender of research in this, said, let's spray. And so that's why we think we have the Papal blessing. So at first I get a little bit in elementary cloud physics. This is about as much as I want, okay? I know myself. So clouds are about 10 micron, right? 10 micron is 10 times 1/10 the diameter of your hair, okay? And they're about, in low clouds, about 100 per cubic centimeter. That's not very much, okay? So droplets need to form around the nucleus, all right? So if you boil water, all right, you will boil water in this cloud room, the vapor pressure of water is gone above the saturation temperature, and you should be forming clouds, and it doesn't. The reason is that when molecules of water come together, they immediately evaporate. So the evaporation of a very small drop is much larger than evaporation that you have, that you're familiar with. So you can't form droplets. Now, if you go Wilson chamber, if you go to the, what is it there in San Francisco? The Science Museum. Yeah, so you see you have a Wilson chamber there, and they have 400% supersaturation, and a particle comes through and it leaves a track. So that, you can actually do that, but typically what we have in the clouds is only about 0.5% supersaturation, right? So that's enough to condense it, but you bring something on it in the droplet, it's sort of, it goes up and down, first in diameter, and it comes in that supersaturation, and then it becomes a droplet that stays there, essentially. Now, if you have a very big crystal, so you put up sort of 2 or 3 micron cloud droplets there, they will become much bigger, essentially, and they will become a droplet, and they will fall out, and they will actually rain out the clouds. So what we're doing is not cloud seeding, okay? That's what you do in cloud seeding, all right? You actually densify the clouds by redistributing the water that's in the clouds. So how do these droplets get formed normally? So, when you have white caps, this basically that's just a lot of bubbles in it, right? So one of these bubbles breaks up. It leaves about 20 little droplets that are just the right size to float up and all that kind of stuff. And that's how most of the clouds form over the ocean. They can also form from algae, believe it or not, like in the, that's what you have in the Southern Ocean, or over, here in land, there's a lot from pollution that we put in the air ourselves. So it's actually a very simple story. So if I have, a bucket that's transparent with glass balls, and the glass balls are 1 centimeter in diameter, you can look straight through it, right? I mean, it'll be deformed, all right? Now, the smaller and smaller I make these glass beads in there until the size of sand, it becomes totally white, okay? So that's what you do with the clouds. You have a certain amount of water in there that's in fairly large drop, and you try to put in more droplets that are smaller. They suck out the moisture from these bigger ones and redistribute it so that you have more surfaces to reflect, and that's what makes it white. So it's a very simple thing to understand, all right? So that was suggested about 90 years, so you see this here of a cloud. You see, for example, that's for different heights of clouds. But you take the line of 150, and you're about 100, oh gosh, maybe I should get my pointer, but anyway, not too far in the top. You can change it by a few percent relatively easy by doubling the cloud concentration of nuclei. So will this work? Well, it sort of seems to work. So we have these ships that are over the ocean, and they burn bunker oil, at least until 2 years ago. So bunker oil, we took all the sulfur out of our gasoline and piled it up on stuff and didn't know what to do with it. And somebody had a great idea, well, we put it in this bunker oil. So bunker oil is 5% sulfur. So when you burn it, you get sulfate particles that are made, and they act just like the particles that we're trying to make, and they leave trails. And that's why you see the trails here. On the left-hand side is the Gulf of Gascogne. On the right-hand side, you can see that is the coast of California, all the white dots there on the inlet. Those are the volcanoes, essentially. And the other ones, these are ships. That's just a simple ship that goes up, gets wider, etc. So that's quite a reflection. And now, so about when this enormous amount of pollution that these ships on there are about 50,000 large ships on each time on the ocean, and about 300,000 fishing ships, which are more like prisons than anything else, but let's not go there. But anyway, the bigger ones are like 50,000. 10,000 maybe of the very large cargo ships. So anyway, so there was a regulation that they had to take this sulfur away. So we no longer have this stuff now. So now all at once, the ocean is becoming a lot hotter. And that's one of the reasons that we think that's part of the reason why we have such extraordinary increases in temperature. So last year, the temperature on the west coast of England was basically 4 degrees C warmer than it was. That is an astronomical increase by any standard of geophysics. And so people have modeled this, and you can see that, just look at the blue and the green. You apply this to about 10 or 30% of marine clouds. And so the top is what you have is, if you double CO2, everything that's red is no good, right? Most of the heating goes in the pole. And you see it becomes a lot greener, essentially, when you actually do the marine cloud brightening. Now, this is a very simple model, and we don't know if it's exactly going to work like that. So as I said, the study of the clouds is extremely complicated to get it right. So how did it get started itself? So, there's been 20 years, 30 years now of theory, and so somebody has to make these very fine droplets, an enormous amount of very small droplets, okay? So I was invited by an Edinburgh conference by Pfizer. So Pfizer is a very small public, private Gates funds for innovative climate and energy. And so they asked me to start an effort here in Silicon Valley, because you can always find guys here that work on very strange stuff in one way or the other, right? So this is sort of mostly a volunteer effort. So this started in the spring of 29, so we got Gates money for a couple of years, and then we ran out of money, and so everybody works for free, and my wife pays the bill, and so everybody is happy. So we identified 3 models, one very promising. We have no corporate structure, and it's a scientific experiment. So for a while, we went in and moved with Xerox PARC, and that looked very promising. It's a very good research organization, at least it was. Unfortunately, we found that we don't want to have intellectual property. Taking patents out of this is very, very dangerous and highly unwanted. So working in a corporate structure that nothing wants but patents just didn't work out. And so we went back to that. So we started a project. We now work with about 5 universities, 2 or 3 here in the United States, another one joining us. We work with Cambridge University, and then we help the guys in Australia. They use our technology for doing the spray barrier reef. And actually, we have had an enormous amount of goodwill and things. So people even that don't believe in global warming, let us use their leverage. This is actually fun to see. So the first thing, the way that you do this is you make very fine holes and you push water through it, right? And then that tends to break up in droplets all exactly the same size. Now, if you have a good ear, a good young ear, and you take a water can, right? And you all these little jets coming out, okay? You can hear them sing sometimes if you get it right. And that's actually coherent breakup of all these little jets, and they give you droplets exactly of the same size. So I did this about more than 50 years ago at Xerox, and I managed to make droplets for 90% monodispersed, which I thought was a big thing. Well, turned out not to be a big thing, but anyway, that's why I was recruited for this project. So anyway, so a number of things that you find out is, so it used to be that making small holes was very difficult, right? So you all remember nylon stockings, right? What was the secret to it? Secret to it was making the very small holes that you push the warm nylon through, and that gives you the socks. So those were called spinnerets. We looked at DuPont. DuPont was the only company that could have under absolute, it was like in a vault, because nobody could see how they made that. So now with silicon technology, making holes is becoming quite simple. Small hole, very small holes. So, we have experts here in the thing. They make things now that are 1,000 times smaller than the things, but the problem is keeping these holes open when there's fluid coming through is extremely difficult. So we actually eventually were going to make a sprayer like this and decided we didn't call the holes open and wanted to find something different. So this got like 2 different, rhodium-plated titanium frames. So that was one of our ideas, still to be a thing, okay. So it got very low energy requirements, that's the good thing. So when you're trying to make these particles, you've got to make it in a method that has 100 million times less energy than the sun reflects, right? Okay. So if you make a cloud that's a kilometer by a kilometer, right? That reflects a gigawatt. That's 10 to the 9 watts. If you go in the stratosphere, there is 1 kilowatt per square meter, okay? It's what common energy. So a kilometer by a kilometer, that's 1 gigawatt. For 1 cloud a kilometer, that's the output of a very large nuclear power plant. That's what that is. So we couldn't keep them open. We decided, smarter people are going to invent that. So then you go to electrospray methods, okay? You probably never heard about this, but so what you do is you can't hold open, so okay, you push water through it, and you pull on it with an electrostatic field, all right? And so now you have a 20 micron opening that you can keep open, but the diameter of what comes out of it is 100 times smaller, and that's exactly what you want. And so very fortuitously, the diameter of what you get is a function of the resistivity of the material that you're pushing through. And seawater just happened to have the right resistivity to put these particles. So you can see this is actually what happened. On the left-hand side, it's so small you can't see it. But on the right-hand side, this is typically what happens with something that's not very conductive. But you can actually pull out single molecules that way, if it's very conductive. And so this is the distribution that you can make of it, and it's exactly the kind of distribution that we want. Now, each one of these little things is about 30 million things, 30 million droplets, okay? So we need about 10 to the 15. So we need 30 million of these little points, okay? Sprayer points, okay, to do that. So people have tried to do that for pharmaceuticals, right? So putting pharmaceuticals, many of the compounds that we make don't dissolve anymore. So in order to get anything in your body when you inject into them, okay, you want to give them an enormous amount of surface, and you make them as very, very small particles. That's what they're trying to do. So that's why they were interested in this. And they got thought, we'd have to do about 30 million of this. So that's not a project for 5, 6 old guys. You know, we actually had all the inkjets from HP guys working with us. But it's outside the scope of what we can do. So we went to other things that we thought was simpler. So this can be done, and people are still working on it. We are actually coaching the university, Cambridge University. So they went to another thing, is sort of, I don't know if you're interested in this. This is supercritical water, right? So you all in water, you know that sort of, you think you know water, right? When you put water on very high pressure and temperature, okay, it doesn't look at all like the stuff that we have now. It becomes supercritical. It becomes a gas, okay? It becomes a very dense gas with about 40% the density of water. But when you normally evaporate water, the gas stays in it. The salt stays there, right? Not in this stuff, okay? That gas contains the salt. It keeps the salt in it, okay? And it has no surface tension. So it's like a gas. So when you spray it, it should spray like a gas, and it does, okay? Very, very fine. Unfortunately, it's extraordinarily corrosive, okay? So the only materials that they can use for it are, as turns out to be, diamond, essentially, for the nozzles, and then you have to gold plate all the other stuff. So that turned not to work so well. Extraordinarily corrosive, anyway. But this is interesting. Unfortunately, the good is not on there. I don't know why. So you see this is all these pictures, okay, is taken by white light, all right? So on above the pictures, the droplets are big, and you have the regular white scattering, all right? What you see in the middle is dark, deep blue. That's why the sky is blue. Because, if you're in the stratosphere, it's all dark. There are no particles there, okay? There's no weather, all right? Okay. But below here, there are particles and gas and all that kind of stuff. And that's why we have Rayleigh scattering. And that's why it's what scattered is what you see and catches your eyes. And so when you actually go fast, small enough you don't get reflection anymore. And I think there's an interesting observation. I don't know. Okay. So stuff to do and too much power is what it amounts to do. So then we now use effervescent atomization. Effervescent is a big word to say basically bubbly water, all right? So you make bubbly water and you spray that. And so most of the food, that if you use processed food, there's anything in it, that's how it's made. It's a very, very common process, okay, in the industry. And so you mix the water and you bring it through. And actually, what you do is if you start with a little bubbles, it goes through that orifice, and then it becomes sort of larger bubbles, and then it becomes a slug flow, okay? And then actually what happens at the end of it, you see that at the bottom, that the water is all clinging essentially to the walls of that orifice, and the gas is in the middle. So when you normally, take a nozzle, you think that all the pressure is dissipated in the nozzle, not in this case, okay? So when you have air, it can't move any faster than the speed of sound. And so when you look on the left here where the nozzle is, that may be at 100 atmosphere, 100 bar, right? 100 times the atmosphere. But on the outset, there is 60 bar in that where it just comes out. There's 60 bar of that pressure is left over. And it takes that very thin shell that's there and blows it to smithereens. And that's how that thing works. So this is so we work at much higher pressure than you normally do. So this is a simple nozzle working on that. That gives 3 trillion particles per second, okay? So for 10 to the 15, we need about 300 of those records. So this is our laboratory setup. It actually had quite you see these 2 big instruments there? They're just left over. We didn't use them, but they look good in the picture, so they look sort of professional. And this is some of our team working on here. One of them unfortunately passed away already. And these are standard instruments that we use. Well, we're not going to make it. What this says is, we thought this works like a charm. It's exactly what we need. So you have this distribution that looks like a normal distribution, and it looks perfect on paper. Well, it took us 2 years to find out that in reality it's not practiced. It isn't perfect. So what you have actually is that the number of particles that you make, 98% are the right size, okay? It's perfect. But the mass of all these particles, okay, they're in the 2 or 3 micron particles. They're only a fraction of a percent of these, but that's where all the mass is. So you're not spraying efficiently, and that's what we've been trying to reduce now for a very long time. So how are you going to get these on the air? So there's a boundary layer over the ocean, and you get these out of them, all right? And so you have to use what you use, a snowmaker, all right? Now, this is different from a snowmaker. You know how a snowmaker works? Some of you snowmaker? All right. So when you ski on artificial snow, you're not skiing on snow. You're skiing on small little balls, okay? So there are 500-600 nozzles in the inside, okay? And then you see on the outside, there are 20 or 30 of them, all right? So the ones on the inside all spray maybe 0.5 millimeter particles, right? Or 200 micron, small droplet. And the ones on the outside that are on the rim there, so you're doing this at freezing temperature. The ones on the outside, they actually spray air and water. And when the air expands, they become much cooler. And so they become ice nuclei, okay? So the droplet that's coming out catches one of these ice nuclei, and it forms immediately a very thin shell of ice, okay? And that's what they hang in the air long enough to fall down and not break, and then you let it freeze overnight, and then you're ready to ski on it. So that's what happens. You see this on the bottom? That's why they sprayed this so far. So it'd be the sort of instrument that we send our particles up, but of course they're 1,000 times thinner and smaller than the ones that you do. So this would be a Moss Landing. That's a perfect place to do that. Normally you have to do this on a ship, but this is surrounded everywhere by marine environment, so that would be an ideal thing. So now we learned from the guys that we helped in Australia, there is another method that's much, much simpler. We hope so. So anyway, people have been working on this for 30 years. And why are they working on this? This is to increase the efficiency of a gas turbine, right? Or a jet motor. So when you have a gas turbine, the large turbines that come in when we run out of energy, or you have to put more stuff in it, and we're going more and more to gas turbines because of natural gas. So there's an axle there, and that on the left-hand side, you have a compressor, right? So that compressor compresses the gas, and it actually makes it hot when it does that. And in the next session, you have the turbine blades, and so the turbine blades for that. Then you have the actual fuel where you inject it, becomes very warm, and then you take the power out, all right? So when you're doing that compression of the air, that takes two-thirds of the energy on that axle goes into compressing that air. And when you do it, what they call adiabatically, which is very fast, okay, that takes a lot more energy than if you could cool it. So if you manage to put in a tiny little droplet of air in that stuff, all right, it will cool the air, okay, and it has to evaporate in a few microseconds because it goes very fast. It will cool the air essentially, and you will have an isothermal expansion. And that increases, theoretically, the efficiency of the turbine by 20 to 25%. And I have to realize that there are many profs at Stanford that have spent an entire career, okay, basically trying to improve the efficiency of a turbine by a fraction of a percent. All right? So it'll be a dramatic thing. So people have been working on this a long time. So what happens is they make this nice distribution by accident, okay? They found this. But there's a tail on it that are bigger particles, okay? And those don't evaporate in time. They hit the turbine blades. You know, these turbine blades are at 500 degrees C. That's not a good thing, okay, to do. So they ruined the turbine blades. So Delft worked on it for 10 years. Then I went to Moscow, to a reputable institute. They worked on it for another 15 years. And so when we take their published results, they look perfect for what we need to do. Unfortunately, you know, there are a lot of other things that make us think that maybe it isn't quite like that. So the way that they measure it and all that kind of stuff. But anyway, it's too good to be true. But that's what we're hoping and working now very feverishly to get this done. So anyway, so these droplets, I shouldn't really, we're going. So basically all this is all what you do, right? So this is a de Laval nozzle. I mean, he said just a little bit of an opening and then a tail on it that makes it wider, right? And so you bring in hot water at 200 degrees C, that's it at 40 bar, and you let it expand. That water is boiling and doing all kind of stuff, and somehow it makes a monodispersed distribution. That's good enough for our work. So anyway, that's what we're hoping. And you can see this is a regular nozzle on the top. This is the de Laval nozzle. And the way that they measure that, you measure the scattering from all these particles in there. That's a very, very difficult proposition. But they use regular water. We use salt. We can let the droplets evaporate and measure what's left over by a regular instrument. So it's much easier for us to do that. But you see a dramatic improvement that when you do this right with a regular nozzle versus this one. Anyway, that's what we're working on. So you see an example here in our own laboratory of what we're doing. So what are the applications on MCB? So it's a perfect tool for cloud studies. That was the original intent. And as time went by, say, well, that's probably not going to be good enough. We're going to try to use this actually for cooling the Earth. So along the coast of California, we tried to get a program going with several other universities when the budget had a surplus, and now it's sort of almost going, but the budget doesn't have a surplus now, and so that disappeared. The Arctic region, where it's another region, okay. So you can try to decrease hurricane intensity, and I'll come to that. Possibly control of El Nino. So the Australians are using our technology to try the Great Barrier Reef, and sadly enough. So the Great Barrier Reef has now been, since 1917, it has bleached 5 times. Okay? So today, as they are actually measuring again and spraying, it's bleached for the 6th time. If the way this is going, and we can't reverse it, by 2030, there's not going to be much left of the Great Barrier Reef. That's the reality. So anyway, so this fossil could possibly be used for global temperature reduction, if things are right. So here is what's happening on the Great Barrier Reef. That's a slide from 6, 7 years ago. So basically, it's now all over. It's a pity to see, essentially. On the right is the Gulf of Mexico, but the number of things. So what we're actually seeing in the hurricane, right, is that the number of them, not necessarily those go up, but the intensity goes up. In fact, we're now thinking of adding a category 6, okay, over 5, all right. So typically what happens, these are these nozzles that they're using essentially, and so it's not a practical method, but it seems to work. These things lift up in the air and they whiten the clouds on a small scale, but it's not yet very effective. So, but this is, for example, Katrina, right, when that came in, okay? What's red is warm, right? That was the Gulf of Mexico when Katrina came on. And so originally, they were sort of not going to get in New Orleans, right? But the Gulf of Mexico, routine low, is now 4 degrees C warmer than it should be, than it was traditionally. So when the hurricanes come in, they category 2 or 3, and they warm up while going over the Gulf of Mexico and become category 4 or 5. That's what's happening. So what can you do about that conceptually? Huh? What you see there on the right is a small fraction of the oil rigs that are there, all right? There are huge oil rigs there, 30, 40 kilometers out, all right? Each one of these oil rigs has gas and all that kind of stuff. You could, in principle, put a sprayer on it, okay? And spray the hell out of it, so to speak, okay? Year in, year out, to keep the Gulf cool, all right? And so people are now that investigating that. The problem is that the Gulf of Mexico is already very, very dirty, so it may not work because we need it sort of to make it change. But you can see this here. I'm not sure very well if you can see the color, but when it came in, this is Hurricane Harvey, right? So it's a different color, and just next to the coast, that's where it becomes red, all right? And that's where it does the damage. Each one of these is a 150 billion blow to our economy. But right behind of it is all our, I mean, that's where all the refining industry is in the US. So that's that people are studying that now, anyway. So let's sort of come to the end of the talk, you know, and it's just leaving you a message that, you know, I'm not without hope, right? I mean, if we keep on doing what we're doing, you know, we're not going to get there. But I think at some time we're going to get our act together and say, you know, look, we can't keep on fighting each other away with all that stuff. But the fact is, this is our planet. We're very, very vulnerable, right? I mean, we only have topsoil, 15 centimeter, over 20% of the earth that's useful. You know, that's all between this and agriculture. That's how little there is. And a lot of it is blowing away. So we've done all these things that we barely missed in the past, you know, so there is no planet B, let me tell you. So this is a picture here of the thing. And so you can see the dark stuff, and then you see the stratosphere, and then you see the troposphere above it. So I listened to a talk of Scott Kelly. That's the guy, the astronaut that was up there a year, right? And he gave a talk at the end, and he says, you know, there ain't no planet B. He says, I came back from a year in weightlessness, and my whole body went to my knees, essentially. Actually, even your genetic makeup changed during the time. So it's well as taken, you know, there's a sense we have all these other consequences. And geoengineering may or may not help us, but it's high time that we do the experiments. And in some issues, you just can't sit on the sidelines. Thank you. There's a microphone there, Shane.
Okay, there it is. It's on.
What are some of the best actions for people in this room, all of us white hairs, to use in the immediate?
Well, you know, the answer has been known for a very long time. You try to reduce your carbon footprint, right? So we put out 40 billion ton of CO2 every year. There are 8 billion people on the world. So equitably, even if we don't go down, you have 5 ton of CO2 to be equitable. I don't know your carbon footprint, but I tell you mine is not 5 ton. Okay, it's probably 5 to 10 times that. So, you know, the first thing is that you avoid using airplanes if you don't have to. Some of us have to, you know, you can't avoid that, but you avoid that because that's a very high carbon improvement. Actually, even cruises, you know, if you go on a small cruise, it's not better than a large cruise. I mean, the number of programs that, you know, I'm not going to tell you what to do. This is an individual choice that the individual has to decide for himself what he's going to do. You know, we have a very large family. We have a very large program. That's the reality.
Is there political action or environmental groups that you would recommend?
Well, you know, I'm not going to go into a political discussion over here in the church, but anyway, there is one candidate that I really lay awake of night for him, because if he becomes president, in my opinion, it's game over. If the United States doesn't take the leadership in this, which he will destroy, okay, this is it. We're going to lose another 5, 10 years, and which we don't have that time.
Thank you for a great talk, Armand. Always great. Geoengineering in general, I mean, it's a wonderful concept. I do worry about the overall impact factors, and do we truly understand them? Of course we don't. You can't answer that question, but that would be my concern, the impact once we make that change.
Well, so what we do, I mean, marine cloud brightening, right? You could do this in the Gulf of Mexico. You make an agreement with Mexico that's good for both of us. You could probably do this here of the Gulf of California and Oregon and whatever it is in Mexico if you want to. But you can't do this stuff up in the stratosphere, okay, without there being agreement and all the people in the world. And we can, and so it's hard to see how we're going to get to that, but, look, I mean, I sort of look back at the pictures that I used to send out during COVID, and I have nostalgia for that time because everybody at least was on the same wavelength. Now we're all divided. But if we don't solve, you can see that historically, right? If we don't solve problems that are lingering on, it's usually the end of that particular society. So that's, so that, I mean, I still think, so we was thinking that every day there are new ideas that are coming out of it. But again, as I say, you have to have global agreement to do that, right? Okay. But, so if we had an experiment that worked on marine cloud brightening, a lot of people would say, hey, let's give this a try, and then all that kind of stuff. So that's it. So for example, this stuff is so attractive, the stuff that we work, is an idea that's suggested by Australia, but it came from Delft. You can actually do this because you only need solar power. You can do this with a solar collector. I can make a solar collector that's 10 meters by 30, so that's about this here, okay? That will drive one $10,000 instrument that day and night sprays, okay? Without maintenance. So, we don't know if that's going to work, but you want to work on it as fast as you can to give people hope and say, yeah, there are solutions. Yeah.
One of the things which you didn't mention are the solar shades, things like that, that prevent the sunlight from reaching the Earth. What about the solar collectors that you just mentioned? I know in Morocco they're sending up huge fields of solar collectors. If we had a bunch of solar collectors that then transform that to heat, to energy, as opposed to heat, would that make any effect?
Well, that's just, we're changing from fossil fuels to, so that's a good thing, all right? Problem is that when we do that, we're going to increase heating, short-term heating, right? Until we manage to get that stuff out. And that is not advertised by most of the environmental groups, right? So that, and you don't want to, but you have to be true to the people when they find out, they say, what kind of nonsense are you telling me, okay? So we have to do it, okay? But it has unpleasant consequences. So when you actually put up all these things now, all right, instead of reflecting sand, which is pretty good reflector and quite white, okay? Now we have a dark you absorb energy too, yeah. None of things that you do, none of this stuff is simple, So people actually, so there were huge forest fires in the Pacific Northwest, right? So they found out that, we're going to have to make these airplanes to bring this stuff up there, right? We have a U-2, but it has no payload. So we have to build huge airplanes that can tons putting it in the stratosphere. So during these fossil fires in the Northwest, they found that you make carbon black, right? That's what you get, okay? But it brings the other particles in the stratosphere. So there is a natural way to actually get these particles in the stratosphere and all that kind of stuff. So, look, we're not going to find a solution, we're too old. But younger and smarter guys will, if they work on this, that's what I think. But it's going to require cooperation. You can do nothing globally without the cooperation of it. And so there are groups already working on this and getting buy-in from the global south that these experiments can be done and all that kind of stuff. Yeah, I work with one of these groups in England, that's been working on this for 20 years. You're going to have buy-in from all the countries. But see, this is the problem with IPCC, right? That you have to have consensus. If one of the fuel states decide they don't want it, they get together with a few and buy out a few others, okay? And they say no. They sit there for weeks deciding about one word. I learned that from Steve Schneider, 25 years ago. That's what they do. Yeah. Look, I wouldn't be working on this, okay, if I weren't hopeful. And literally.
How big is your group? And what's the median age of your group? I hate to ask that, but what is your group?
Well, it's a sort of geriatric group. We're in and out of the hospital, and we work on it as we can. So that's part of it. So we were down to 5. I know David Beagleson, who is actually here from Ladera. So he's recruiting a lot of the fine people from Park. So we doubled in a few weeks into double, actually. So people are now saying, oh, yeah, there's wrong with an exercise for 40, 50 years from now. We're going to need this, or we at least got to look into it, yeah. Yeah, we're called the old salts, for obvious reasons.
Another question. I love the marine cloud brightening concept. If you had infinite number of ejectors to put the seawater up into the stratosphere, what does the wind currents do as far as where it's going to end up globally? Are you going to end up it being concentrated on various areas so that some parts of the world are not going to get...
No, the individual particles will fall out locally in it.
Right, but in other words, are they going to... You've got the Coriolis effect so that the winds go different ways.
You do this in low-hanging clouds. You can't get up to the clouds that are 10,000 feet high.
But globally, if you had millions of these injectors...
To be calculated. Yeah, you're right, to be calculated. It's like the windmills, okay?
Right.
You put up enough windmills, that's got a global effect on the drag.
But what I'm wondering is whether or not parts of the world are never going to get shielded just due to the wind currents.
Yeah, so you can only, so what's actually happening, we start thinking that you can do this. So traditionally it said it won't work over the Atlantic Ocean, all right? So then one guy looked for where all these shipwrecks are, and they're over the Atlantic Ocean. You just got to look for them, yeah? They're where the ships are. So now we start thinking, oh, maybe we can do this other area. So the way that you would do this, you give every 50,000 ships of the ocean, okay, you give them a sprayer. And you tell them to turn it on when they want it, and they get some carbon credits for this. Yeah? It's a simple solution. And they put it in the chimney, it's going to go up, it does it now, yeah, so that's going to work. We can do that for experiments because the guy wanted to be pure. They don't want to contaminate this with other stuff that's in the cells. So we have to make our own spray, but normally you just inject that in the stuff and it's going to go up in the air. Yeah.
Can you add it to the airplanes?
Well, so we're talking about two different things, right? So another application, for example, is that you can spray certain things that go in, you need a very fine sprayer, okay? And you spray iron trichloride, okay? And that's a catalyst for changing methane into innocuous compounds in the air. So it's a catalyst. It doesn't get eaten, okay? And it just so happens we're there with a water company that sort of treats water. That's one of the specialists, iron trichloride. So a number of applications that people are thinking about there, all of them are risky, and you have to find out, and that's why you got to do the experiment. But we're in a much better position to do these experiments now. So EDF now has like a global tracker of methane, right? Methane is by far hashing. So methane, when it comes fresh out of the ground, it's about 100 times more absorbing, okay, than CO2. But it only lasts 20 years, okay? So effective, lasts 80 years. So it's basically, it's 20 times more effective in general than doing that.
Okay. Yeah. Dr. Armand, thank you so much for spending your time to come here to tell us about this.